Okay, so this is lesson 20, and what we're going to do is we're going to take a little break from intersections today, and we're going to start talking about distance formulas. So we're going to do a few distance formulas. The goal is mostly in R3, but we'll see one example in R2, something that you would have seen in the past. And I don't think it's, it's too difficult to imagine why we want to know some distance formulas. So, classic example is if the tip of my finger represents the Earth and this represents the motion of, say, a meteor that's passing, you do want to know what's the closest it is going to get to the Earth. Okay, so again, not surprisingly, when we talk about the distance between something like a point and a line, well, I'm not even going to bother asking because we all know. So we assume that it's the closest distance where it forms a 90-degree angle. Okay, so these are some of the distance formulas we're going to take a look at today. And then next week, we're going to focus in on the last big intersection problem that we have. And similar to what happened in grade 10, when you were studying intersections of two lines, in other words, solving two equations and two unknowns, that the techniques that you developed to solve the intersection of two lines then was useful in determining solutions to any system of two equations in two unknowns. And of course, in this case here, I'm talking about linear equations. In grade 11, you then expanded that to solve linear quadratic systems or quadratic systems. All right. So let's start with something you already know the answer to. Okay, so I'm just going to ask you to sort of come up with the formula and give me a brief justification as to why this formula is valid. So let's officially give a distance formula between any 2 points in R3. Okay, so I'll give you 30 seconds to write that down and to give me a quick justification. All right, so who can give me the formula for this distance between these two? Okay, and we have someone there that we realize that it's just going to be the square root. So if you look at your chat, somebody typed it out for us. Okay, it's just going to be the square root of the square of the differences of each component. So x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared. Okay, and what is our justification for that? So why did we not have to come up with a formula for this? Why can we just write this straight away? In what context did this come out, which is equivalent to finding the distance between 2 points? Okay, so who can give me the justification why I'm able to just write that out?
Because the vector between the two points is just the x2 minus x1, y2 minus y1, and z2 minus z1.
Exactly, is that if I form the vector joining these 2 points, the distance between the points is equivalent to the magnitude of the vector. Okay, now notice here, because all of these are being squared, does it matter whether I connect them this way or that way? And the answer is no. So had I written this formula as x1 minus x2, y1 minus y2, etc., it would have been perfectly fine. Okay, so again, there was no need to reinvent the wheel because we know that the distance between the points is equivalent to the magnitude of the vector joining them. Okay, and again, as we've sort of referenced before, this is very nice because it's just a direct upgrade from our distance formula between 2 points in 2D. All right. So let's move quickly on to number 2. And this would have been kind of one of the big ticket items of grade 10 analytic geometry. Okay, probably would have been one of the longer problems you would have solved. This idea of finding the distance between a point and a line in 2D. Okay. Now, does anybody remember what the process was? What was the process that you had to follow? Because you had to do a few things here. So if you had this point and this line, what did you have to do to determine the distance between these two objects? Does anybody remember what the process would have been? So I'm pretty sure you would have had to at least find the equation of this line or be given the equation of this line. Okay? And think about what's special about this line that I drew, which joins the point and the line. What is special about that segment? We're thinking too hard. I even put it straight on. Okay, it's normal. Okay, let's use grade 10. You know, this is good now. I'm glad we're using these grade 12 this grade 12 vocabulary. But if you think back to grade, yeah, there you go. It's perpendicular. And of course, if I know the slope of this line, I can find the slope of a line that's perpendicular to it. So once I have the equation of this line, I can find the negative reciprocal, which would give me the slope of this line segment. What would I do now with the slope of this line segment? Anybody remember what the next step would have been? What can I do once I know the slope of this line segment? Remember, I have this point. There you go. Find the equation of this perpendicular line that passes through that point. Once I have the equation of this perpendicular line, what would you do next? There you go. Solve the system to find the point of intersection. And then once you have the point of intersection, you could use your distance formula to find the distance between the two. Okay, so it was quite an elaborate process. Okay, took a fair bit of time, probably took, 2/3 of a page to complete, and would have been one of the longer problems that you would have solved back in grade 10. Okay, well, what I'm suggesting here is that if we work with Cartesian, the Cartesian form of the line, where now we recognize AB as representing the normal vector to this line, that maybe we can come up with a better formula. Okay, so what I want you to do is think. I'm not going to give you too much time, but just sort of think about how we might set this up. Okay, and I'm trying to think of what hint to give you without giving it away too much, but this is maybe too big a hint, but I'll just give it to you anyways. Okay, it's going to involve a projection. Okay, I want you to think about how you can set things up. So assume that you know the equation of this line, all right? And you know this point. So if you know the equation of the line, you know the normal vector. So how could you use the idea of projection to determine this distance? Okay. All right. So we're back. Let's see if we can come up with a strategy. So I gave you the hint about thinking about a projection. Okay. Kind of gave you some hint here that the normal vector might be involved. So any ideas on how I could use a projection and maybe use this normal vector? Okay. Because again, remember that this distance that I'm looking for is drawn so that it's perpendicular to the line, and the normal is also perpendicular to the line. So how can I bring these two things in? Any ideas here? Okay, let's think about this. Is that I know that this normal vector is in the same direction as this distance that I'm trying to measure, okay? So if I could somehow project something onto this vector so that it gives me exactly that distance, that would be, yeah. So, we want to try to project a vector, but problem is what vector am I going to be projecting? And this is where we're going to use a little trick, is we're going to say, well, let me pick any point on the line, okay? So let's say xy represents any point on the line, and I produce a vector to the given point, okay? Now, if I find the projection of this vector onto the direction vector of the line, okay, if I was working with, say, the vector equation, that doesn't give me anything useful. So what projection should I be producing here in order to get the distance? So I think I can produce a projection with this vector here, but onto what vector? There you go. Is I'm going to project this vector here onto the normal vector. Because remember, the normal vector can move. So if I move the normal vector here, and I project this vector onto the normal vector, that distance is the same as the distance between the point and the line. In other words, the distance that I'm looking for is equal to the scalar projection, okay, of, well, whatever this vector here is. So if I call this point Q and I call this point P, okay, it's going to be the scalar projection of the vector QP onto the normal vector. All right. Now, any questions as to how I got this? So I just moved the normal vector to this point here, and I projected this vector. You know, I can imagine putting my flashlight here, and I found the shadow that it creates in this direction. And so this distance here, the scalar projection, is going to be the same as the distance between the point and the line. So any questions on that before I move on? Okay. Now, if I just leave I could just leave the equation like this, you know, because I know the normal vector. Here, did it matter whether I took this point or I took that point? No, the scalar projection would still give me the same amount, the same distance. The problem here is this, you know, I'm trying to, yeah, so remember, we're assuming that the line is given in Cartesian form, and if the line is given in Cartesian form, well, you definitely know the normal vector, right? Because A and B just represents a normal vector to this line. So yes, we assume that we know that vector, all right? The problem here is there's still quite a bit of work because I have to choose some point on the line, meaning I have to take the time to figure out a point on this line. Then I have to create my vector, then calculate the scalar projection. And so there's still quite a bit of work to do here. So what I think would be worth doing is let's see what happens when we see this through. Let's see if we do some algebra and if we can simplify this equation a little more. Okay, so now, by the way, why am I taking the absolute value of this scalar projection? Does somebody want to remind me why I have to take the absolute value of the scalar projection? Okay, this is good review on projections. Why did I have to take the absolute value here? Yeah. And what do we know about scalar projections? Okay, there you go. Is that the scalar projection could possibly be negative if it's, you know, going in the other direction. Okay, but we want this distance to be a positive number. Okay, so let's go ahead and find the scalar projection. So what is the scalar projection? Okay, so it's, you know, qp dot n, so n dot the vector qp divided by, now what am I dividing it by? Which vector? Who's going to tell me which vector I have to divide it by, or the magnitude of which vector I have to divide it by? Okay, this is good review of projections here. Which one goes in the denominator here? There you go, the vector that I'm projecting onto. So over the magnitude of n. Okay, so again, let's just do the algebra, see what happens. See if anything interesting happens. So the denominator is already positive, so I can split this up into two absolute values. One, you know, the one and then keep absolute value in the numerator, and then the magnitude in the denominator. It's already positive. So let's see what we have. We have AB, okay, dot. So what would QP be equal to? Well, second minus first, so it's x naught minus x. And then here we have y naught minus y, okay, all over. Magnitude of n is just going to be square root of a squared plus b squared. Okay, let's keep going. Okay, this is still, you know, a fair bit of work. So let's do this dot product here. So what do we have? We have a times x naught minus x So that's ax naught minus ax, okay, then plus, multiply this here, by naught minus by, okay, all over square root of a squared plus b squared, okay. Can anybody have any idea what I'm going to do now? And I want to remind you here that xy is a point on the line. What do you think my next step is going to be here algebraically? I'm going to do a little, nothing special, but something that's going to be quite useful. There you go. You know, we've seen this trick before where we kind of group together terms that are similar. So I'm going to group together ax naught, okay, plus by naught, okay. X naught, y naught is not on the line, okay. But then I'm going to group together negative ax minus by. And now I want you to tell me what is special about negative ax minus by, remembering that xy is a point on this line. There you go. Let's take this equation here, and c is equal to negative ax minus by, okay, for xy on the line. And xy is on the line. So this whole thing here is just equal to c. And look what we get. A very nice equation. But I want to talk about why it's very nice. What are the only things we find in this equation? X naught, y naught, which is the point we're finding the distance to. So presumably you have that. And a, b, and c, which are just your coefficients in the equation. What do you notice does not appear in this formula at all? That's it. The whole point on the line thing, when you do the algebra, just disappears. All right? And so what you have now is a very simple, okay? So what used to take you, 8 minutes to do if you were, quick at doing analytic geometry, now literally takes you 30 seconds because it's just a times, now not an x value on the line, but the x value of the point you're finding the distance to, plus b times y times the y value of the point you're finding the distance to, plus c, all over the magnitude of the direction, the normal vector, okay? And this is about as nice as it comes, folks, in terms of taking something which is a long geometric process and turning it into a very short algebraic process, okay? So we're really starting to see here the power of working with all this stuff algebraically, okay? Now, this is fine. This saves you some time, but of course, why I would spend so much time working this out when my focus in this course really is on 3D. So this is kind of a nice little result, but I'm thinking we might be reusing this concept again in a little while. Okay, so what used to be a long, arduous process back in grade 10 has now been reduced to just plugging in a bunch of numbers. Okay, so what I want you to do is I want you to just, essentially, it's a straightforward application of this formula. There's no need to go through this whole process. That's the whole thing about showing a proof, is that once you've shown that the distance can be given by this equation, because this didn't specify a particular point, when we used xy, we used any random point on the line, and we got to this equation here. Okay, so just quickly apply this formula, and I'll come back in less than a minute to take it up. All right. Okay, so real quickly here, now the idea is, do you memorize this formula? Well, in principle, yes, you do. Okay, it's you could definitely go through this whole process every time. Okay, certainly can, but it's such an easy formula. Okay, because in the end, you're just inputting this point into the equation of the line that it's worthwhile just knowing the formula. All right, so here the distance is just going to be, well, it's given by, so what's my equation here? Oh, what's the problem with my equation? Okay, so what's the first thing I'm going to do? Because I've got a direction vector and I need a normal vector. What's the easiest way to take this direction vector and turn it into a normal vector? There you go, is flip them and make one of them negative. Okay, so if my direction vector is -6, -2, my normal vector, well, I'll choose to make the first one positive since I prefer having the first one positive. So 2, -6. And then once I have the normal vector, I also have a point on the line. I can easily, oh, even better, of course. Good thinking there. Who's that, Samya? Good thinking, Samya. I might as well take an even nicer one. I might as well just take that 1, -3, so I don't have to simplify later on. Okay, and so now I can solve, bring in my point. So I have a times 2 plus b times y, which is 4. Whoops, which is 4. Okay, plus c equals 0, and so c is equal to, so what do we have? 2 minus 12 is -10. Bring that to the other side is going to be 10. And so now I can use my formula. Okay, so it's a times x naught, which is -3, plus b, okay, which is -3 times my y value, 5, plus c, which we just determined was 10. Okay, all over the magnitude of, where's a and b? A and b, 1, -3, so 9 plus 1 is 10, so square root of 10. Okay, and so what do we have here? We have -3 minus 15 is -18, plus 10 is 8. Sorry, -8. Take the absolute value, it's just going to be 8 over square root of 10 units. Okay, and if you want, you can find an approximation for that. Okay, or you can rationalize it if you want to avoid the square roots in the denominator. Okay, so in the end, what you want to try to remember is that the distance is given by the absolute value of the given point inputted into the equation of the line divided by the magnitude of your normal vector. That's sort of the easiest way to kind of remember the formula, okay? Instead of remembering it as a series of letters, okay? All right, so I'll give you a bit of time for this one here, because what was the issue with lines in 3D? That we couldn't really treat it in a similar way to those lines in 2D, at least the way we've defined the line in this Cartesian form. What is the problem with kind of using a similar setup as we just did in number 2? Who remembers why we weren't able to use that similar setup? Why are we not able to work with a normal vector? There you go. Is that there's no one direction for a normal vector. Okay, in 2D, there's only one direction for a normal vector. Something along this line here is the only direction for a normal vector. As soon as we go to 3D, well, that could be a normal vector. This could be a normal vector. This could be a normal vector. There's just too many directions. Any direction could involve a perpendicular vector. So that's why we can't use the same idea. Okay, so we need to find an alternative for this distance, okay, I would say that that's a pretty good hint there that somehow, you know, this idea of bringing in the area of a parallelogram, okay, might be useful. All right. So let me leave you a minute or two to think about this, okay, and think about how we determine the area of a parallelogram. Okay, that's the big hint here. All right, so we're back. Did you just notice I changed the Q to a P? I think I'm just going to stay consistent with my notes. I'm pretty sure in my notes I have this one designated P. So I'll just stay consistent with the notes. All right, so I'm suggesting here that we might use the area of the parallelogram to help us determine this distance. All right, now, problem is I don't have a parallelogram. So can anybody tell me how I might produce a parallelogram? And what this distance would have to do with the parallelogram? Yeah, they are. Rectangles are definitely parallelograms. So here I see draw two lines. Okay, let's be a little more specific. What lines would I draw? Oh, so remember, I can't use a normal vector because there is no normal vector to a line. Because remember, this vector here is perpendicular, but I could also have a vector coming out. Okay, so somebody is suggesting here, what about doing something similar to what we did in number? Yeah, in fact, I don't think we're even going to need a projection here. Because remember, well, we'll talk about that in a second. Okay, but I like that idea of taking some point Q on the line here. Okay, and if I create the vector from Q to P, what other vector do you think I'm going to use here to create my parallelogram? Because remember, to produce a parallelogram, I need two vectors placed tail to tail. Well, what if I also use the vector M, which of course I can take vector M and move it anywhere I like. And all of a sudden, I realize that this produces a parallelogram. And what is special about that D value? What does it represent with respect to this parallelogram? It represents the height of the parallelogram. Good. And, well, wait a minute. What would the magnitude of M represent with respect to this parallelogram? The base. And somebody seemed to indicate that, well, if I have the base and the height of a parallelogram, I can calculate its area. And of course, what other way do we have to calculate the area of a parallelogram? Somebody just said it a second ago. We just have to take the cross product of these two vectors. So if I take the cross product of QP and the vector M, it gives me the area of the parallelogram. And then if I divide by the base of the parallelogram, that'll just give me what remains, which is the height, which is equivalent to the distance between the point and the line. Okay, so here I have the area of a parallelogram. I don't know what parallelogram here. I'll use that for area of a parallelogram is just base times height. And here, the distance that I'm looking for is just equal to the height, which is just equal to the area divided by the base. Okay, so what we have here is the distance is equal to the area of the parallelogram. Okay, now in this case here, we have to be careful because it's not quite the cross product. What is it? Because the cross product gives me a vector. What do I have to take with respect to that cross product? That gives me the area of the parallelogram. There you go. I'm going to take the magnitude of this cross product of QP cross M, okay? And I just have to divide that by the base, which is the magnitude of M, Okay? And here, would it have made any difference if I picked that point and created a parallelogram? And the answer is no. Okay, because even if I picked that point and created a parallelogram, this would still represent the height. If I take this point and create a parallelogram, this still represents the height. Okay, so here where Q is any point on the line. And what's great about this is that lines in 3D are given by vector equations, and so that's always going to possess a point on the line. Okay, so while we weren't able to eliminate this idea of actually picking a point on the line like we were able to do in this point to a line in 2D, where we could not ever use the point that we choose, here we do have to find our point. We have to find this vector, then we have to find the cross product and do the division. So there's, a few steps in the process, but again, it's a fairly simple process. All right. So again, we're starting to see here how we can make use of, something that didn't seem that important, finding the area of a parallelogram, not saying can't have some importance, but this is where this connection to the geometry of the cross product is coming in very handy for us, okay? Because the distance from a point to the line is definitely something of importance for us, okay? So I'm just going to ask you to apply this formula to this scenario here. So a little bit of work to do, but go ahead and complete that. Unless there's any questions we want to ask before going to that. So take a look here. Now, of course, the idea is you don't have to develop this every time. Having said that, the development is fairly simple in case you happen to forget, how we come up with this formula. Okay, so I'll give you a couple of minutes to finish this one off. Okay, we're back. I just didn't realize how late it had gotten, so let's do this one quickly so we can move on to the last thing for today. Okay, so here, let's just quickly figure out what we have. So there we go. We're creating this vector from the point on the line to the given point. Okay, so what I'll call our QP is just going to be, what do we have? We have 2 minus negative 2, which is 4. Then we have 1 minus 7, negative 6. And then negative 5 minus 3 is negative 8. So make sure you're checking my algebra here. And then we want to take the cross product of that with the direction vector, which is negative 3, 4, negative 2. And so let's see what we get with the cross product. So we get 12 minus negative 32. So 12 plus 32 is 44, I think, 44. Here we get 24 minus negative 8. So 24 plus 8 is 32. And then we've got 16 minus negative 18. So 16 plus 18 is 34, right? Okay. So now my distance is just the, oh yeah, which one did I get wrong?
The very last one for Z, it becomes positive 18 and then minus again though, right?
Oh, good call. Thank you. I wasn't being careful there. Good catch there. So this is 16 minus 18, because it's going to be positive. So 16 minus 18 is negative 2. Thank you. All right. So let's take a look. Our distance is the magnitude of this cross product. So the magnitude is going to be 44 squared plus 32 squared plus negative 2 squared divided by the magnitude of the direction vector, which is negative 3 squared plus 4 squared plus negative 2 squared. And just to save myself from having to simplify this, I'll just find an approximation for it. Okay, let's try to get it so we can see it. So here, what do we have? We have square root of 44 squared plus 32 squared plus 2 squared. Okay, and divided by the square root of 9 plus 16 plus 4. Okay, and that looks to be at about 10.1 units. Okay, so again, a fairly, easy process, little more work. It's not just a matter of having an equation where a formula where you can just stick some numbers in. There is some work to do, but still relatively easy. Okay, so the last thing, and I'd like to have you try to come up with this yourself, because very similar to how we worked with the Cartesian equation of a line in 2D, and then we were able to use the exact same formulation for the Cartesian equation of a plane in 3D, well, guess what? You should be able to do the exact same thing with the distance from a point to a plane instead of just the point to a line. Okay, so I want you to just, again, we're running a bit out of time, so I'm going to leave you a little bit of time here to try to start the formulation yourself. I think you can probably, guess as to what the final formula is going to look like, but I would like to give you a little bit of time to work on that. All right, so let's go through the formulation here as quickly as we can, and essentially I'm going to be doing a carbon copy of what I did before, because everything else remains the same. Is that I know I have this normal vector, this one direction for a normal vector that is perpendicular to the plane, and this distance that I'm looking for is perpendicular to the plane, so I do the exact same thing. I take any point on the plane, say x, y, z, I create my vector, say I call this point Q to point P, and I just move this normal vector here, and I'm just finding the projection of QP onto the normal vector. Okay, so this projection is the same as the distance from the point to the plane. Okay, and this is just my scalar projection. All right, so this distance is just the absolute value, just in case that scalar projection is negative, of the vector QP onto my normal vector. And then everything else looks exactly the same, because this is now just A, B, C, dotted with QP, which is x naught minus x, y naught minus y, z naught minus z, all over the magnitude of the vector I'm projecting onto, which again is the normal vector, and then I just follow the same procedure. Ax naught minus ax plus by naught minus by plus cz naught minus cz. Okay, all over square root of a squared plus b squared plus c squared. Okay, and as before, I just group together all those terms with the x naught, y naught, and z naught, and I group together the terms that involve the point x, y, z on the plane. Okay, negative ax minus by minus cz. And because this point is on the plane, all of this is just equal to d. Okay, so we're assuming that we're working with a plane with this equation here. Let's bring all that to the other side. There you go. And lo and behold, you have a formula that doesn't involve this random point on the plane. Okay, it involves just the equation of the plane and the coefficients of that point. So you just end up with ax naught plus by naught plus cz naught plus d, all over square root of a squared plus b squared plus c squared. Okay, now wait a minute, what if this point happened to be on the plane? What would you get? Yeah, because then, hey, if x naught, y naught, z naught is on the plane, then this whole thing should be equal to 0, which of course makes perfect sense, because if the point is on the plane, then the distance between the point and the plane should be 0. Okay, so let's just quickly do this example. So again, what's nice about what we did is that we did all this work not considering a specific plane, a specific normal vector, a specific point, meaning that now it's just a matter of applying this formula. Okay, so now when I'm looking for the distance between a point and a plane, okay, there's no geometry to consider. I can work purely algebraically with this formula. Okay, so what do we have? We have 3 times -1 minus 4 times 2 plus z, which is 5, plus 6, which is our d value, all over the square root of 3 squared plus 4 squared plus 1 squared. So what do we have? We have -3 minus, -3 minus 8 is -11 plus 15, -11 plus 5 is -6 plus 6 is 0. Oh, lo and behold, what do we end up with? 16 and 9 is 16 and 10, 26, and there you go. That's equal to 0. Okay, so we can, assume at this point here that -1, 2, 5 is on the plane. Now, if I wanted to, what could I have done beforehand to check that this was the case? If I had any suspicions that this was going to be the case, what could I have done? There you go. Let's plug in the point and let's confirm that it's on the plane. Well, -3 minus 8, -8 plus 5, -3 minus 8, -11 plus 5 is -6 plus 6 equals 0. Okay? Not necessarily something you think of doing, and certainly if the numbers are any bigger than this, you probably just don't even bother because the formula is so simple. But again, as always, the algebra will take you to the answer, okay, even though there might have been some intuition that could have come into play. If you do the algebra correctly, it shall always lead you to the correct answer. Okay? So that's the end of this lesson.